We've been given an overview of the organization of CERN. Now we will get an insight into the hardcore technology. Sergio Bertolucci is research director, and he will introduce us to the machinery, the tools, the projects that CERN needs for the type of research it does. So after this, the introduction by Paul Davies, we will look at the practical side of physics, which is necessary for theoretical physics as well. And I think it's wonderful to have experts like Sergio Bertolucci here with us. So we're looking forward to your presentation. Thank you very much. My German isn't too good, so forgive me for speaking English, even though my English isn't that wonderful either.
It's a pleasure for me just to be here, and essentially most of my job has already been done by the previous speaker in a very nice way, I must say. And so I'm left with some few remarks. Particle physics sometimes is seen as a very immaterial and a bit expensive way in which people are looking at science. As a matter of fact, as it was very beautifully explained by Paul Davies, the only way in which we can try just to catch some of the things that we don't understand, and there are many things that we don't understand about universe, even the one in which we are living in, is just to try just to go back in time in such a way that we can look at it when it was, and we think, is an assumption also, simpler than it is now. And that's why we are forced just to build this huge machine, which in turn will allow us just to get this millionth of a second after the Big Bang and reproduce particles and situations which are no longer available in a universe which has become complex and cold. That's why, despite the fact that we are perceived just to be very abstract, we are doing one of the simplest way of science, because we are restricting ourselves to the most elementary part of things. So it's called elementary particle physics. We are smart. We try just to get into the simplest way. Systems is much simpler than biology, for instance, or any other thing about research. In order to do that, we have just to be very material. So if in one sense we are looking at big paradigm changing, so we are the people who would like just to bring candles to electric lamp. Now, if you make candles better and better, you'll never get to an electric lamp. In the middle, there is the electrodynamics. You have just to discover Maxwell's equation, and then you build the electric lamps. But we understand that in order just to get to this paradigm shift, we better make better and better candles, because we have just to use all the best technology that we can in order just to make our experiment. And the history of mankind has shown that whatever looked immaterial at some point, it became very useful later on. And there are famous stories. Faraday was visited by a minister also at that time were financing research. And the minister was looking at all his gadgets and experiments and said, well, it's very nice, I'm very impressed, but what's the use of that? And Faraday was honest enough just to tell him, I have no idea, but I know that one day you'll put a tax on it. And he was right. And the same goes with antimatter. You have heard that Rolf Landois has made his scientific career on antimatter. You would hear after that Michael Dozer talking about the beautiful thing we are doing with antimatter, with this. And of course, everybody of us has been exposed, at least for a number of minutes, to angels and demons in one way or the other. So antimatter looks very, very material. And of course, in 1929, when Dirac found this equation, which had a very puzzling solution, and one of the possible solutions, if you were accepting that the equation was right, was just to infer that for every elementary particle there was an antiparticle. At that time, it looked absolutely abstract. Nowadays, it's saving our lives when we take a PET scan. The positron emission tomography is using the antimatter of electrons to save our life. So as Paul was saying, in order just to understand, we are living now in a very nice period because we can put together the same type of question if you look at big scale at a small scale. At big scale, we have learned just to make beautiful detectors that we are here on the Earth or we can send to space, which are looking and taking picture and not simulation of just traveling back in time by looking at distant objects. With the accelerator, we are doing this beautiful microscope, which are addressing the same space and time travel, just going the other way around. And our dream is just to take this ruler, which spans many orders of magnitude, 60 orders of magnitude, and bend it together, bring it the two ends together, because this essentially will give us the answer, the next answer. And we have, you know, science differs deeply from religion because science is not the worshipping of truth. We are worshippers of doubt. We know that whatever is the next thing that we discover, which will answer some of our questions, this will open more, and we hope, deeper question for going on. So that's why also, since we have not unchangeable truth, that makes us very easy just to work together beyond barriers of religions, nationalities, and things like that. And CERN is a beautiful example of that. We have 90 nationalities represented at CERN in this moment. As Rolf was saying, there are many reasons why we should not be happy. Imagine the status. We have a beautiful theory, which essentially we have tested up to a level of 1 per mil, which tells us that we have all the basic components for building a universe like ours, and all the basic forces just to keep it together. And we need just to discover a couple of things, like, for instance, this Higgs boson, because all these components, in principle, they should be all equal and have zero mass, be all like photons. As a matter of fact, they are ranging from something which is very light to something which is as heavy as a nucleus of gold, and still are elementary particles, are point. So there should be a mechanism which creates the mass, and the mass is one of the most elusive things, the origin of the mass is one of the most elusive things that in our research since a long time. The problem is that this model is starting just to be unsatisfactory because we know that it cannot be the last one, for a number of reasons. For instance, some years ago, we have discovered that neutrinos, which in this model are massless, have mass, because they change their flavor. They oscillate from one, for instance, from being a neutrino electron to a neutrino muon with a certain frequencies, and that can only happen if they have mass. We have discovered, for instance, that gravity, as it is now, cannot be described by definition by a similar theory, because you cannot incorporate gravity into the standard model. We have discovered even more, so that we only know a small amount of what is out there, because not very many years ago, 10 years ago, as a matter of fact, it was completed, this survey of the universe and this analysis of this fluctuation, of this beautiful picture of WMAP, and this was telling us that all the matter, all the energy of which we are made and that we see around in the universe is only 4% of what is out there. Then there is a 26% of something that we call dark matter, for which we have ample evidence in different ways, because we see, for instance, from places where there are no brilliant objects, we see that light is being lensed. It makes not a straight line, but there is some gravitational change. And there is even a more obscure thing, that's why we call it dark energy, which is accelerating the expansion of the universe. And this energy is 70% of what is out there. So it's clear that we have many questions in front of us, and particle physics is addressing them from the other point of view, from the point of view of the origin. And and we have a solution also for that, which, of course, needs just to be proved by experiment. Solution could be that, for instance, for every particle in this world, there is a partner, a supersymmetric particle. Imagine that you decide a symmetry connected to the angular momentum of this particle, and then there is, for every fermion particle which have a semi-integer spin, there is a partner, a supersymmetric particle, a sort of specular world in which essentially you realize the symmetry between matter particle and forces, which is a big thing. And this could be, if the lightest of this particle is stable, as it should, it could be the origin of dark matter. And we might create this type of particle, which, if the explanation, should have existed at the beginning of the universe inside the LHC. There could be, as Paul Davies was saying, that we are in one of the possible universes, and essentially we are trying just to write a theory in a world which is not the real one. Imagine if you would try just to describe an elephant, just taking section on a sheet of paper. It will depend very much where you cut the elephant, what kind of theory you write. And because the elephant is a thing which lives in more than 2 dimensions, and would be very difficult just to have a complete view of the elephant in 2 dimensions. Imagine that nature essentially lives, let's say, in 10 dimensions instead of 4. And also, if you think that this is very abstract, think that 100 years ago, we were thinking that we were living in 3 spatial dimension of space, and that time was totally separated to that. Slightly more than 100 years ago, Einstein told us that these things are essentially forming a 4-dimensional space. And nowadays, this simple thing is, for instance, inside our car navigator. Because if you don't put in your car navigator the fact that the satellites of the GPS of the system are moving at a certain speed, and the Earth, which has a mass, is also distorting the propagation of light through the space-time lines, you would be off-road 170 meters every second. So, I mean, you have just to use relativity in Einstein and 4-dimensional space-time just to go and find your favorite shop. Anyway, there are even more theories on that. But of course, the hope of any experimentalist, I am an experimentalist and not a theorist, is that nature is giving us some evidence so different of what we expect, because at the end, one big part of the research is not only just to look to the known unknowns. Higgs boson is a known unknown. We have postulated it as one of the mechanisms which could give mass to all the particle, so we are looking for it. And if we find it, we are just to study it, just to understand what we found is what we were looking at, but in a sense is a known unknown. Suppose that we discover something that we don't even think about that. One of these funny fishes coming up in the thing. That could be the thing which brings the field even further than we expect now. Anyway, the good thing about LHC is that we know that whatever is the answer, it should be in the scale, reachable by this machine. That's why this machine is not just, fundamental research is always an high-risk environment, in the sense that if you knew what you were going just to find, you would not do it. So you have just to accept the fact that you might start for making the next step, and the next step essentially is empty. There is nothing there particularly different. But in this case, we have evidence from all the measurements before that this model has just to either be confirmed or collapse totally at the energy scale which LHC can explore. And that's why we built it. It was a very long enterprise. We were slightly cheaper than what Paul Davies was saying. We costed only 6 billion, not 8 billion, but still is a big thing. And it took us 20 years to conceive, build, because at the time in which it was conceived, most of the technology used for building it was not there. So we had not only just to build the machine, but just to develop the technology. The most important development was, there is always this picture of this, looks like a gas pipeline. Is a very sophisticated gas pipeline because is 27 kilometers of superconducting magnet, which are capable of very high field, a Tesla, which could be built industrially. And this development has caused immediately a fallback, a transfer in the society, because now most of the superconductor used for magnetic resonance machine is following this type of development. The machine is one of the coldest places in the universe. You heard that this WMAP thing that tells that the universe has a temperature of 2.7 degrees. The temperature inside the LHC is less than 2 degrees, which is minus 271 degrees Celsius. It is very empty because in order just to not to have this beam of protons go around and hit residual gas, you have just to remove all the gas. So at the end, you have there a pressure which is 1/10 of the atmosphere that you would find in the moon. And of course, when in the place where you are hitting these two beams of protons, the temperature, the energy there is 1 billion times hotter than the center of the sun. So the LHC is the microscope. You need the eyes just to look at that. And the eyes are not only the only important thing, is the eyes just to look at it, and then you need the brains just to interpret it and just to keep it in a memory someplace. And the experiments which have been built there are again a remarkable feat of human ingenuity, because they are at the same time very complex, at the same time beautiful from point of view of their they're exploiting symmetry, they're exploiting easiness of interpretation. They are as lean as possible, although there are 100 million channels type of camera, capable not only of making 40 million pictures a second, but every second looking at these 40 million pictures and retaining only the 300 which are interesting, and for them just store them in their memory and analyze them. These experiments have been built in also a way which has changed the way which physicists usually were used just to work in the past, in which essentially we're trying just to make things not always with the best engineering, because we wanted just to be fast and thing. If you are building something as complex as Atlas or CMS, and you build it in 25 different countries, you have just to be very, very good in engineering if you want that when you bring things together, they stay together. And the thing stood together very well. There were moments of apprehension. I was reminding last night that, for instance, one thing, then when we put down CMS, which, you know, in one single piece, a piece of CMS which was weighing more than 2,000 tons was put down 100 meters down from surface to the pit. And people forgot that LHC is not totally perpendicular to gravity, because when the tunnel was excavated, in order just to avoid hard rock at the Jura, it was tilted by a few degrees. So when the thing arrived and they released the thing, they made clunk, because there was not, and people had forgotten. They had remembered other things and forgotten this one. And the experiments are, in a sense, specialized. There are two big experiments, which are general purpose experiment, Atlas and CMS. Austria, for instance, had an important contribution to one of these experiments in the conception and in the construction. And then there is another which is more specialized, because we can collide in the same machine also lead ions. We take atoms, we strip away the electrons, and then we throw these two nuclei ones against the other, just to form another very interesting constituent of the early universe. At later times, not 1/1,000,000th of a second, but much later, 1/1,000,000th of a second after the Big Bang, the world was a soup of quark, free quarks, and gluons. And this quark-gluon plasma is a very interesting object to study, because it will tell us again how then nuclei formed and how matter is like it is now, and probably cast some light into all these parameters, these 30-odd parameters of which Paul Davies was talking, which they look so fine-tuned that if you change it in one part in 10 to the 50, nothing will stay again like it is now. Then there is another experiment which is specialized in looking this slight asymmetry. You know, we don't understand why we are here, because at the beginning, if everything was coming from a Big Bang, the amount of matter and antimatter should have been the same. And most of matter and antimatter annihilated immediately after, as you have seen in Rolf's movie, and we are, all the universe around us is what is left from a very small asymmetry between matter and antimatter. And we don't have yet a satisfactory explanation of the magnitude of this asymmetry. We have mechanisms just to study it. It is one of the things that we are keeping studying in many different ways, including a specialized experiment at LHC. So, of course, I will jump a bit on things, because it would be useless at this point just to show you how well these experiments are doing. The experiments are working now. They're keeping working until the end of next year, and then we'll go into a maintenance period, after which the LHC will double its peak energy, or if you want, just make 1/2, cut 1/2 of this time just to go nearer to the beginning. And essentially, I want just to spend a few words in another thing, which is, in my opinion, a big achievement, which allows a thing like LHC to work. As you have heard from Rolf Landois, we have, CERN was the place where the web was first implemented, was used, was invented. And the web, there is sometimes the confusion. The web is not networks. Networks were existing way before the web. But the difference was a change of paradigm, because in the network you were moving information from a source to a user, to a destination, and or sending information from a place to another place. The web has allowed every node in a network just to become user of information and provider of information. And that has changed our world totally, completely. If you think that nowadays it is guessed that about 10 to 15% of the global production of wealth is caused by the web. An evolution of the web is that instead of using only for information, you are using all the computer in the world, or a number of computers in the world, as computer, also just to do computation, to store data, to analyze information in a coordinated way. And this is made possible because networks have become so powerful, the geographical network have become so performing, that you can explode a computer in the network. And this is what the grid does. And it is clear that we need a sort of a thing, because these experiments are producing so much information that if you were writing the information they're producing a year, last year the experiment have produced 15 million gigabytes of data. So if you would be writing them on CD plates, you will make a pile of CD 20 kilometers high, or on DVD as high as Mont Blanc. So you need just to have a smart idea how just to get to analyze all this information. This is the grid. In this moment that we are talking here, there are about 200,000 computers in all the world, geographically in all the world, which are looking at the data of LHC and analyzing them almost real time by processing almost 1 million jobs a day, and by having a sustained traffic, which is every second, as everybody in the world in this moment would make 20 telephone calls. So it's a beautiful thing that is happening, and again, is migrating outside this field, and is having already a big impact in biology, where people are using the same scheme just to recalculate proteins. We'll have a big impact in the future, in my opinion, on general health. Because everybody of us will have the possibility just to have all his record being kept and accessible to himself and to the curing doctor or to the researchers. This is one of the other things that immediately can migrate to the society. So I want just to conclude, because we are in this moment in a very exciting time. These experiments are running beautifully. LHC is running beyond any expectation. These machines are very complex objects. So at the beginning, immediately after the start, as you remember, there was an incident just to remind us that this was not a common object. We fixed it, and now the coming up of the machine is so fast that nobody could really believe beyond our most optimistic expectation. And the experiments are keeping up with that, because the experiments are also very, very able just to follow the growth of the intensity of this machine, and they are ready in any moment just to make discoveries. We have in front of us now a clear task. By the end of next year, we will have solved the problem of the Higgs boson one way or the other. Which in both cases will be a big discovery. If we discover the Higgs boson, we will have first of all just to see whether it is the one predicted by the Higgs mechanism or the one predicted by other theories, so we'll have just to study. But it will be a big discovery because we put a cornerstone in the standard model. If we prove that it's not existing, which is different from not discovering it, we have essentially destroyed the standard model, and we know at this point that in the energy reach of LHC, something else has to happen, because otherwise there will be things which are not consistent with a conservation of probability, say so. So we are even more excited. And sometimes people say, well, you know, it's easy just to, if you discover one thing, and it's more difficult just to convince people that you have discovered something if you don't find something. And they use sometimes this way. I mean, suppose that you are fishing, one of these famous fishes. You can go fishing, you can go fishing in a fair way. You buy a line, a hook, you put a bait, and you wait there. And after a while, if you catch the fish, you're happy. If you don't catch any fish, you're left with two hypotheses. Either there is no fish in the pond, or you are a lousy fisherman. We are probably not fair fishermen, but we don't want just to be lousy fishermen. So we are fishing in a different way. We are removing the water from the pond. At the end, if the fish is there, we will be seeing. If there are no fishes, we'll say there are no fishes in the pond, and that will be a big discovery. Thank you very much.
Who has still some questions? Or are you totally overwhelmed by the amount of physics? And okay, another scientist starting the questions.
I'm Dietmar Kuhn from Innsbruck University. If you say that time arises in an Augustine manner with the creation of a universe, and on the other hand, you say that we have a puffing up of universes, it means the last process has to be embedded in a time scale. So the creation of time must be something locally, and you have a general time governing the popping up.
There we are. Yes, I'm sorry if I confused you. So when I was a student, it was generally believed that there was just one universe with a Big Bang and that that was the origin of time. And that may still be the case. But in the last 10 or 20 years, it's become fashionable to suppose that there are many Big Bangs. And so within our universe, we have our own time, but if you stand back and take a God's eye view at this multiverse, then that would have no beginning and no end. So there would not be an ultimate origin of time. There would only be a beginning of each individual universe. So these are two different models. One is one universe with time beginning with the Big Bang, and the other is an infinite number of universes with an infinite time. And there may be other possibilities we haven't explored. So I hope that clarifies the point.
Another question over here.
Sort of two questions. In the multiverse model, are there any constraints on the possible conditions of laws of physics that a meta level among all of those universes? And second of all, is there any possibility of communication or knowledge from one universe to the other?
Those are both excellent questions, and which I deal with in my book called The Goldilocks Enigma. Let me take the second question first. There are many different ways you can have a multiverse, but one that is very popular, it's called eternal inflation, has the bangs going off like this. And each universe you can think of as like a bubble, expanding very fast, but the entire superstructure in which the bubbles are appearing is expanding much faster than each bubble. So although the bubbles are expanding very fast, they're conveyed apart much faster than they expand, so they almost never intersect. It's possible to have some models in which they do intersect, and then people look for things in the sky, but mostly they don't. And also these bubbles in this particular eternal inflation are so enormous that it is likely that the distance from where we are to the edge of the bubble is, 1 followed by millions of zeros. Now the question about the multiverse, and I think this you I think have touched upon a really, really important question, which I try to bring out in what I've written about this, which is that the job is not finished just by saying, well, there's a multiverse, because there will be meta laws in that multiverse. And in particular, I showed a little slide with a puff, 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 a universe-generating mechanism. So in the typical fashionable models that people use for a multiverse, they will assume quantum field theory, for example, and general relativity. These are assumed to apply in this as meta-laws in this bigger system. Now we can ask, well, where do those laws come from? And supposing those laws were different. And the ultimate, if you want to take that to the ultimate extreme, you might suppose that there are all possible laws on all possible universes. There's only one person that really takes that seriously, and as a matter of fact, I've just spent the last few days with him in Copenhagen at a conference on this sort of stuff, is Max Tegmark from MIT, and he believes that all possible mathematical relationships are out there somewhere, and so we can imagine not only laws, not only universes that obey a restricted set of laws, but all possible conceivable laws. That's the extreme point of view. Really, in this game, you can make up the rules.
Again, for Paul, I guess, since we're on this run right now. I read your wonderful book, The Eerie Silence, last month. And, of course, that relates quite a bit to the Goldilocks phenomenon and is another set of big questions that I think tie in very well. So maybe for the benefit of the audience, you can say a little bit about those ideas.
Yeah, the Eerie Silence addresses the question of, are we alone in the universe? And I wrote it to coincide with the 50th anniversary of SETI, the search for extraterrestrial intelligence. I've been involved with that in a small way for many, many years, and I chair something called the SETI Post-Detection Task Group. Would you believe that there is such a thing? It was founded by the International Academy of Astronautics, and it's a weird collection of scientists and journalists and a couple of philosophers and science fiction writer and a lawyer, and we deliberate upon. Can't hear. Can you hear now? We deliberate upon what we would do. I often say that if ET calls on my watch, I should be the first to know. So this book really is, in a way, a celebration of SETI, the Search for Extraterrestrial Intelligence, but also a wake-up call to the scientific community that we shouldn't just leave it to a small group of radio astronomers to look for signs of intelligent life elsewhere in the universe. We should look right across all of the sciences for any signatures of alien technology. In other words, instead of restricting to messages, sweeping the skies with radio telescopes, hoping to pick up a message from an alien community, which is what the SETI project mostly does, we should instead forget about messages, but just look for any way in which advanced alien technology might impact its environment. Maybe it's planetary environment, more likely it's astronomical environment. And I've given, in the book, go over a list of things we might look for in addition to radio messages. So that's, briefly what the Eerie Silence is about.
Hello. Hello, yeah. Rob Lafrena, curator, Arts Catalyst. Didn't get beyond A-level physics. One for Paul Davies. You mentioned towards the end of your talk the role of the human observer in the universe, and I wanted to pick up a bit further as we're at a festival which considers things like machine consciousness, this sort of thing. Why is the observer, and this applies to some of the discussions in quantum theory, is the observer human? And what is the difference between the human observer and the machine observer, whether or not it's operated by a human?
Yes, thank you for the question. I didn't mean to imply there's anything special about Homo sapiens as such, our particular species. I wanted to draw the distinction between being a mere observer and being able to understand what's going on. The point is that this multiverse explains why the universe looks so well suited for life, merely by supposing that in those universes which are bio-friendly, there will be observers who will wonder, well, I wonder why the universe is so fit for life. It's a selection effect. And it is merely necessary to be an observer, to be a selection effect. It's not necessary to actually understand anything about the universe. But we, human beings, have come to understand the universe from science and mathematics. You don't have to necessarily be human. We happen to be the only intelligence we know that understands the universe. I have great admiration for the gorillas and the dolphins and the long-lost Neanderthals, but they haven't come up with E equals mc squared. They haven't built rockets and gone to the moon. And so it may well be that we will create machine intelligence that will be even better than we are at understanding the universe, and that doesn't change the argument. The truth is that nature has produced, through the emergence of life and its evolution and the emergence of consciousness and observers and so on, at least some beings who have come to understand the deep subtext of nature, the mathematical rules on which the universe runs. And there may be other beings out there, for all we know, who have also come to understand the universe. It didn't have to be so. We could imagine a universe which is observed and is not understood. But we've gone beyond that. So I think there's still a mystery to explain. There's a link between at least the human mind and maybe the minds of the proverbial little green men and the nature of the universe, which is not captured just by saying they're all possible laws and they're selected in the bio-friendly ones.
Derek de Kerkhove, University of Naples. One thing that was not described, and I'd like to hear more about it, and maybe Sergio or Paul can answer, is the appearance of life depends apparently on the explosion of a specific type of supernova. And I was wondering, as all the elements have come one after the other, after helium and hydrogen, I'd like to know more about why that particular supernova was required to create the possibility for life.
Right, I'm acutely aware that my fellow guests here have sat politely in silence, and perhaps they'd like to tackle. I'm happy to answer, but I'm happy to defer to either of you. There is a long story about how life came to exist, and I think everybody here will know that carbon is the important life-giving element, and carbon wasn't made in the Big Bang. It was made in large stars which formed later on. And it's because stars are nuclear reactors, the cores of stars are nuclear reactors, and that's where the carbon gets made. It's long been said that our bodies are made from the ashes of long dead stars, or nuclear waste, if you like, depends on your point of view. But the thing is that if the carbon and the other elements life needs remain inside the stars, then that's no help. They have to get out somehow. And one way they can get out is through a supernova explosion, when a star blows itself to bits and the outer layers of the star are spewed out into the interstellar medium, where they can become incorporated into the next generation of stars and planets. And so I mentioned that the solar system is about a third as old as the universe. There were many stars and planets around long before the sun even came to exist. And the early stars made the carbon, which became scooped up in our solar system and is now inside our bodies. And so this mechanism of getting the carbon out of the stars involves one of these other coincidences or fine-tunings I was talking about. And this time it has to do with neutrinos. Neutrinos, we don't see them in everyday life. They're extraordinarily penetrating. Most neutrinos, for example, the sun is a prolific source of neutrinos. Most of them go straight through us and through the Earth and out the other side. So we don't have to worry about neutrinos penetrating our bodies all the time. There are millions or billions and billions of neutrinos every second going through us, and we don't fret over that because they just go straight through. They don't cause any damage. And you might think, how have we come to know about neutrinos? They're just so weakly interacting. What are they for? Well, it turns out that when a star explodes in a supernova, what happens is the core of the star implodes very rapidly on a time scale of about 100,000th of a second. Boom, it's just gone. It implodes from something the size of the sun down to maybe something the size of the Earth, or even the size of a city in this tiny fraction of time. And so the matter is so enormously compressed that even the neutrinos now have to struggle to get out. And it's this is part of the mechanism that blasts the material of the star into space. So if the neutrinos were even more weakly interacting, they come straight out of these collapsing stars like they come straight out of the sun. They would have no effect. And if they were more interacting, they wouldn't get out at all. But they seem to be just right to disseminate this material around into space. And because that dissemination mechanism is so crucial for life, clearly the strength of the coupling of neutrinos to matter is part of this life story that has to be just right. Otherwise, there would be no carbon-based life, at least.
I think we have now questions for several more hours of discussions. I again have to be the bad guy and try to keep also the timing that was made very well up already by the scientists. Please use the chance also to raise questions and discussions after this session at our lunch table. There are many more other opportunities during this week. This is just the beginning. I think we rather should make now our little coffee break, because we have much more heavy stuff to digest in the morning session and especially in the afternoon. Thanks very much to our speakers. Thanks to the audience for all these interesting contributions.